Okay, I think we can get started. I want to thank everyone for joining in on this week's Smart Webinar. I'd especially like to thank our guest speaker, Dingxiao Cao. Hopefully I didn't butcher your name too badly. He's the Data Science Manager at WPXI Energy. He has more than 15 years experience in data science and advanced analytics not just in the energy down or upstream area, but also with Anadarko, with BP America, and in the automobile industry with Ford Motor Company. He's going to talk to us today about Internet of Things, real-time analytics, and machine learning and operators perspective, and some of the work that he's doing with WPX now and that he's done with Anadarko in the past. And without further ado, I'll turn it over to Dingxiao. Thank you.
Thank you for the introduction, and thank you for Gavin's invitation. Very honored to come here and to share what I had done in Anadarko and also what we plan to do in the WPX. So actually, the title I changed a little bit. Right now the new title is the Digital Transformation Journal, the IoT real-time analytics and machine learning, but the materials is all the same. So this is actually the outline. So first, I will give you guys some base concept about some of the terms, like the digital transformation, like the IoT, and also edge computing. And then after that, we will go to the Anadarko use case. So all the materials we are talking about here actually is based on my paper in the past 3 years with Anadarko. So it's public. It's about a paper and cover the RTD and RTC. And so we will talk about the architecture, the models and the challenges and the results. So the idea is like, actually in Anadarko, I worked with a team to build this RTD from the scratch. I mean from scratch. Actually, me and the developer work together, and I also write the Java code or Python code line by line to make this happen. And after that, actually, they asked me to lead the data science effort of the RTD and RTC domain. So actually, the real-time computation system, I didn't build that, but I focus more on the model side. So we will talk about the model here. And then after that, I will talk about the real-time analytics strategy we have right now in WPX and what we're going to do in the next 1 or 2 years. So that's the big highlight. So first, if you have any questions, just stop me and ask me. But I will just go over because I have about 40 slides, so cover a lot of stuff. So just stop if you have any question. So the background, the first one is the digital transformation. Maybe I think you guys already know this one. So digital transformation is a big, very broad one. But from my perspective, like upstream oil and gas, what I more focused on is like I try to digitize all the undigitized information, like in oil and gas, you know that some of the oil company already 100 years old, 80 or 60 years old. A lot of the documents in the PDF, in a paper, some kind of stuff. Some of the information is key for our model to go through. So that's one of my focus. But the general one is like digital transformation actually is like to get the data, put the sensor, and then do some predict analysis or visual analysis, that kind of stuff, and build an app. So this is the general term. Another one I want to say is the IoT, because this is very popular right now in the industry. Here you can see the picture actually is to put all the sensors in each of the equipment in the house so that you can talk to the equipment and also you can collect the data and then so that you can manage or analyze the data. So for oil and gas, actually the same, you just put the sensor to the wellhead, that kind of stuff. So this is easy to understand. And the last one I want to talk about is edge computing. So this one actually is my focus on the WPX right now. It's because it's very important. This is actually, like today we are talking about real-time decision making. So this one will enable us for true real-time decision making or even a closed-loop control, because data come from the side, and then if you push to the cloud to do computation and push back, they will have some latency. and also that is not actually a real-time decision. So here I will talk more about this one in the next slides. But the most important for the edge computing is you need to have the hardware, like the box in the website, and also you need to have a platform so that you can do a stream analysis or like the data processing. So I mean the platform actually is like the Kafka or like Spark streaming, that kind of, you can get the stream out and processing the stream. So that's actually is the edge computing. So the next one, we will go to the use case, the real-time viewing. So first, I will give you some basic architecture of the real-time streaming system, and then we will go through the first generation and the second generation, and then we will talk about the digital transformation strategy, because this one is very important based on my feeling. And then we will talk about some ML model, but the ML model we build here is more in a practical view. So as long as the model can solve the problem, we are good. So it's not in research perspective. So it's a simple model, but it's useful, solve the problem. So here is the architecture level. You can see that we built two versions of system, from the first generation to the second generation. So the second generation actually address all the challenges we have for the first generation. So that's why. And then this is the base element of the real-time system. What kind of real-time system, you will always have 6 pieces, like the data source, the data collection and managing system, real-time processing, and then all these 6 pieces. And here, when we talk about the real-time viewing, actually is the source of the data source actually is in RIG, right? We get the victim connector, we get the Kafka to get the data, and Spark streaming. Right now, the Kafka also can do the data processing. This is actually the 2 years old picture from my paper. So, and then you have the database to put the result, and then finally link to the UI. So this is the pipeline. And then this I put here is the open source one. Solution, and then also in Anadarko, I say we build everything in Streambase. Streambase actually is a software we bought from TIPCO. It's a software company. It's a streaming platform. So, but it's very expensive. So, but we build everything on top of this one. So this is the architecture, and then go to the next one. There's the fourth generation system. So we, in Anadarko, actually we POC with 3 months at 2017, and then we had a lot of challenges when we deployed it into production, because we suffer from the data digitalization. What does data digitalization mean? So let's put it this way. Let's say, if you have model, you need a file input, but when you have a system running, you only have 2 input available, or another 3 input actually is in a PDF file or in an Excel file in somebody's computer. It's not in a database you can use immediately. So what I say digitalization is actually we need to have some workflow to actually get that data and make it available so that the real-time system can use it. Otherwise, the model is not working. So that's very important. And then another thing we do actually, we build some simple engineering model, not a fancy MLDL model, it's just a simple calculation. So this is another view of the system. So you can see from here, victim connector, and then you go to the analytics layer. So that's we pull out the model here. You can see, and then finally we go to database and go to the UI. So it's similar to what I put in the previous slide, but it's a more convenient way to see it. And also here we also can hook up with the static data. The on-prem database, you can see that the on-prem database actually is like the OpenWell or like a WellView had this kind of well name, well API number, or like say the BHA information, the whole information, that kind of information is very important for the model. So that's the whole architecture for the first generation. And then go to the second generation. So actually we address the challenge of the first generation. It's because the first one is the more function of the fixed space model, because we don't have data. Like I say, 5 input, you only have 2. So that one we call it a digital transformation solution. We build some application to do that. And then like before I said, we build some simple engineering model, but it's not very good. So accuracy is very low. So we use the MLDL to solve the problem. And the last one, we build a ML pipeline in the cloud, but that's not a focus today. And another thing we want to mention in the second generation is like we have good UI. Actually, believe me or not, in 2 years we built 5 versions of UI. So the UI is very important. And this is the second generation. And actually, this is the architecture. You can see it's bigger because the ecosystem, we call it the ecosystem because they have multiple pieces right now. So the original one, you can see this is the original one. We still have the orange, that's a streaming system from here. And also we have the model here, all right? So, but we add this piece, the yellow piece, and also we add the green piece. The green piece actually is the ML pipeline. I will not talk into detail today. If you're interested, you go to the paper to take a look. It's the ATC last year's paper. But here, that's digitalization transformation app. Actually, is we build some application, try to digitize the information and save in the database. So when the real-time data come in, then it's ready. And then, like, let's say here, the fixed-based model, like the Toll-inject model or the hydraulic model, they need a lot of static data. That actually come from here. Otherwise, it's not working. So that's the whole architecture of the real-time system. And then talk about the digital transformation strategy. So actually, I think that this is very important. And then I think this is back to the nature definition of the digital transformation. That means we actually transfer the data from the paper-based or some other base to a digital. It makes it ready for real-time to do. But at the same time, we also try to optimize the workflow. So one of the examples is like, let's say, this is a dueling program automation tool. As you guys may know, before we do a well, we need to prepare a document like a dueling program. Let's say it's a 100 pages of the program. You need to prepare the program and then submit to the government so that they can approve so you can drill a well. Similarly, when you want to build a house, you need to do a lot of paperwork so you can build a house. So prepare this dueling program actually is related to a lot of information we can collect. So in America at the time, this program actually is like people use a Word document and template and copy paste. Like they need an API number, they go someplace, copy the API number. If they need a BHA information, they go to some place and copy and paste into there. And finally, they generate as the PDF file. And that's a manually work. And it takes the engineer maybe like 5 or 10 hours to prepare one well. But at the other side, we don't have the information. Let's say we want to run a Toll-inject model, or we want to run a hydraulic model. We don't know the BHA, we don't know the pi information, we don't know the whole information. But it's all here, all right? So what should we do? So actually what we did, we build a tool for them. So let's say, okay, we build a tool for you. If you just key in a well name or well API number, we try to go to different database to grab the information on all the field there. And of course, if the information is missing, of course, you need to key in the information because they need to prepare the drilling program. So in this way, and when they fill in the information, they are ready, then they hit the button to generate the PDF file. So their drilling program is ready. And for our side, when they hit the button, we collect the information, and then we dump to the database here. And then finally, we can use to do the Toll-inject or like hydraulic model. So that's we call it the digital transformation. We built 2 tools at the time. And then this actually is a Toll-inject. You can see that Toll-inject, I'm not sure you guys had the background. Toll-inject model actually is like a very important fixed-based model in the drilling. Toll actually is like when you drill a well, you move the pipe up and down, that actually is the drag. And torque, that means when you rotate the pipe, that actually is the torque. And that's why real-time is important, because we want to do the calculation every when we're drilling. We want to see the measurement of the hook load is matched the model prediction. If they are not matched, that means they have some problem, and then we need to stop and do some more circulating, that kind of stuff. So this model is very important, and it's an old model, but it means real-time take a lot of effort. So at the time, and then we go to the ML DL model. Let me see what time is right now, 18. MLDL model. So in the MLDL model, actually we built two models. One is we call the slide rotate model, and another we call the Downlink model. I will give a detailed introduction in the next slide. And we deploy the model into the system 24/7, running inference. Every single second we send the data to the model, we get the result out, and then so that's the way. And for the rotate slide, as you guys may understand that when we drill a well, the rig has a lot of states, like the rig activity here. Look at here. So every single second we have the data coming. We want to quantify what the rig is doing. Are they doing drilling? Are they doing circulating? Are they doing shipping chip out? So in this way, we can generate a KPI. Okay, say, oh, okay, 50% of time you are doing drilling. Wow, that's great. But another one maybe 20%. But in order to do this, we need to categorize them into different states, right? And all of this is all the states. And almost all of them can use the rule base to do so. So we say if else, we can get majority of them. But two of them is very important, and it's harder to get is the slide and rotate. So this is why we use the ML to do that. So of course, at the beginning we use a rule base. We build a rule to do it, but the accuracy is very low. So actually, we try to use the traditional method, like the random forest, to do that. Random forest is good, but not very good for this basin. And DJ is good, but otherwise not good. So we go to the CNN. Of course, and the CNN is good. Convolution network is very good. And then when we build this tool, we want to deploy it. We find out it's too complicated to deploy two kind of model. So okay, why bother we build another CNN for this DJ? So actually we build two CNN. Of course, we remove some of dependency. One dependency is like the section, like the vertical, curve, and lateral, something like that. And finally, we say, okay, well, this CNN is so powerful. Why bother we build one model for three basins? So finally, we build a general model for three basins and without any dependency. So that's the evolution of the model. And here actually is the architecture. You see the random forest is here, the CNN is here, hybrid CNN RNN. From the accuracies, yeah, here you can see this is actually the random forest is not very good for the Delaware Basin. CNN is good, CNN RNN is good. And here for the DJ Basin, even the random forest is good. And go to here, so we use the CNN, it's all 99% accuracy. So, but here I want to say something about this one. So the CNN RNN model and the CNN model, their accuracy is almost good. But finally we deploy the CNN is because the computation cost. Computation cost, that means the inference cost. Like, as you know, this is a real-time system. So the data come every single second. And you need to get the result out as soon as possible. But I may take 5 seconds to do the inference. So that will cause some problem for the system. Imagine this way. The real-time system is like a highway. Every single second, we had the data coming. And similar to highway, every single second, we had a car go into the highway. And the model actually is like a toll gate. And if the car come to the gate and take more than 1 second to go through the gate, then actually you will have the traffic, right? So like the car pay the tollway and then get the receipt, and then they need to wait for the receipt, and then so this will have the traffic in the behind the toll gate. The same for the model. If the model is more than 1 second to inference, then the data will congest in the system. So that's a very important message when we deploy the model to the real-time system. More example in the later I will show you. So that's why we use the CNN for this one. And the next model actually is the Downlink model. Downlink, actually, I'm not sure everybody know the Downlink. Downlink actually is like is a rotary steerable system. When you want to give the command to the beak, to tell the beak that your one is to drill up, drill down, drill left, drill right, then you need to send a command. But we cannot send an electronic command. That's why we need to send a command based on the pattern. Let's say the port. Here is like the port, and they have the pattern. And then when you send the pulse down, this is standpipe pressure. And then in the beat, they can recognize the pattern and then say you ask is to turn left, turn right, turn up, turn down. So that's why we want to quantify this one. Is because the junior engineer want to see who did a good job, who did a bad job. So let's say for the same well, if you use the 20 downlink to do the job, and another guy used the 15, that means you didn't do a good job. Similarly, when you drive from home to office, you turn 100 times, other guy just turn 80 times, maybe 80 times, that other guy will save more energy. So that's just the business really behind this one. Of course, this look like very simple, right? This model, you just need to identify this one. This is the downlink. So there are a lot of methods can solve the problem. Like at the beginning, we try to use the traditional signal processing method, like the change point detection model, like this one. And then it looks simple, right? This is very good. You can find the change point every single time. So this is the change point. But actually, it's not that easy. They have a lot of issues. First is the change point detection, detect every single change point. So it's harder to identify whether it's downlink or not. So that's one of the reasons. And then because of this one, and then we try to use another method, like we use the UNet. Like actually, we consider the UNet and LessNet. It's a pre-trained one. So actually, we made this as an image transmutation problem, and we convert the time series data into an image. So like here, this is image, and then we mark the downlink in a pixel level for target segmentation. So image segmentation actually is very mature in the let's say the medical field. They're very good to analyze the X-ray picture, that kind of stuff. So that's one of the reasons we want to use this. I know that there are tons of methods can solve this problem, and a lot of people told me that you use a big knife to kill a mosquito. But my goal is like we want to solve the problem in 2 weeks, and we want to make to production as soon as possible. We cannot source too much method. As long as one method can solve the problem, we don't care whether it's a big knife or small knife, as long as it can kill the mosquito. So actually, we use the open source code, and then we label our data. We train the model, and finally we get a very good result. So actually, like this one, the image segmentation, they actually can give us the downlink, also the duration, so that the F1 score actually is very high. You can see from here is actually we also here we use the 10 well. It has the RSS, and another 21 well we don't have the RSS because our real-time system is blind to the BHA. We don't know which kind of BHA we have. So we even if the motor well still send the data, the model still perform good. You can see that we add the 21 motor well, and the false positivity is not that high. That means if they are not downlink, it's not a downlink. They don't identify the downlink. So this model is very reliable, and then we put into production. So I think we are done with the RTC. So yeah, we actually for the RTD side, we do build a lot of other model, but we are only these 2 or 3 actually is the ML model. That's why I present here. And then go to, let's see what time we have. 27, I still get time. So the use case is real-time completion. Real-time completion, first I will give you guys the architecture. And then hydrofracture 101. Hydrofracture 101, I know some of you may have background in hydrofracture or some may not. But I just give an introduction so you have the base knowledge so that know what kind of program we want to show here, use the model. The RTC model, actually, we have 5 models here. We have the state, start, and even recognition. And also, we have a model to identify the ball seed. And also, this one actually is we want to segment each state. We want to segment segment the states, and so that we can get the meaningful KPI. And the next one actually is the wellhead pressure. When we want to predict the wellhead pressure when we do the fracture. This is actually try to predict the screen out and to pay the foundation for the next model. Like we really want to do real-time completion cost optimization. Actually, this is all our work. This is a big cake. We do all of this stuff because we want to do this. But without doing this, we cannot do this. So actually, this is in a series. And also, we want to automate RTC data pipeline. That means from the beginning to the end. We don't want too much human being to manually label data, something like that. So that's the idea behind this model. So the same for architectures. Similar to what we have in the Downlink side, you can see that we have fragment, and then I think the remaining is the same. Only the first two is different. Data source and data collection is different. But the model is still put here. And then, of course, this is the open source example. In Anadarko, we don't do it in this way. So actually, in Anadarko, we do in a cloud-based system. So we put everything in the Google Cloud. And we don't have as computing power. We cannot deploy model at the data van. I will tell you why we needed that one. And here is the architecture is a symbol. The data come in. The streaming actually is the data connection, like the pops up, and the processing, the model put here, and then go to the data warehouse is the database, go to UI. Here the on-prem database actually is the open well or some other statical data, like I said before. So this is the overall architecture. And then 101, I just give an overview, like say, yeah, when we frag the well, we plug. We run like the toe stage. We will just frag. First, we need to perforate. Okay, we perforate. Like here, we perforate, and then we frag. We frag, and then the next stage we need to run the plug. And right, we run the plug here, and plug this portion. Not yet, and then we perforate this portion, and then we run a ball. The ball all the way down here and plug here, so we can isolate this stage, and then we can just flex this stage, and then the next one is like come back, run another plug, and then do the same thing. So that's the simple high level hydrofracture. So here what we do is like we build a model to identify the stage start and end, and also we want to identify when the ball is sick here, so that we know the actual fracture is start. So that's the idea. And then this is the start end. You can see this is signal. You see one actually is the slurry rate and one is the Welhead pressure. I think the red one is the pressure. And then what we want to do is like we want to build a model to identify the start and end. Because in Anadarko, actually at that time we had people sit there and manually label this one. It's painful. And of course they had a bias and also not consistent because your label and my label is maybe different. So that's the business value, motivation behind this model. We want to build a model, just plug in the system so that it does the job. We don't need any people to label the data. So when we try to build a model, we put it as a classification model. So you can see we label the timestamp to 0 and 1. 0 actually is outside of the stage, and 1 is inside the stage. And then, so the star will be 0 became 1, that's a star. And then 1 becomes 0, that is the end, right? So, and then we slide the window. This is a signal we have, slurry rate and Welhead pressure. Of course, we have some derivative. So this is six signal. And actually, we buffer the data 50 seconds, and then we change the model. So moving the window like this. So that's the data preparation. And the model actually is very simple. It's just a 5-layer of CNN model. But the result is super good. So yeah, this is the feature 6, and this is time moving, so you predict output. And when we talk about the matrix actually is like, when you talk about in a second level, it's very demanding. There are two kinds of, one is the timestamp, and another is the flex wise. I will talk about that one later. When we want to evaluate the accuracy, one way is like, you need to exactly 0, 1. That's really tough. Even the human being, I label, you label. Maybe I label 1 second behind, you label 1 big deal because it's really tough. Like if I label right now, I label if my mouse slide a little bit, then we go to another second. You can say so. It's very demanding for this one. And another one we call the flag-wise accuracy. That means we give a tolerance window as long as you are in the window, either behind or ahead or behind. As long as you are in the window, we consider you are good. Your predict is good. So this is actually very practical. The computer engineer say that 25-second window, that's a 50-second, should be okay. So here's the sum of the result. You can see them. If you put the tolerance window to 25 seconds, then you will get a 99% accuracy. But if you reduce to 3 seconds, that's a 70. I think if we go to this one, is 60, something like that. But when you use your eye to see, it's not that much different, right? So it's a true is a blue one, and that one is a prediction one. You see that. So this is the result. Actually, the result is very acceptable. So this is one of the model. And another model is the ball seed. Ball seed. Not all the operators use the ball to plug the stage, but another use it. So that's why we built this model. And we try the business motivation behind this is we try to find the actual flag start point, and then so that we can generate more accurate state-wise comparison KPI. For example, let's say some states they don't have the ball seed, some states have the ball like this one. But if you want to compare them, you need to remove the ball, pump down and seek them, right? Because from here you pump the ball down and you seek here. So the actual the flag actually start from here to the end. So if you want to compare, you need to use this one to here instead from here to here. We had people to manually label this one also in NETL. So that's one we want to build a model to replace the human tedious work. When we examine the data, we find it's funny that we find that there is a pattern in the story rate because of E pattern. A E pattern is very obvious. And then we think about the Downlink model. So the Downlink model actually is actually an image segmentation. And then we think maybe that model can solve this problem. So actually we use the same model as the Downlink model. And we try to use the image segmentation to get the Z pattern. So it's a two-step strategy. Tell if there is a ball seed, like if they had a E, then we say there is a ball seed, a ball. And then if once they told us, then we use the rules to locate the ball, the end of the ball seed. So this is this actually is the mark look like this, the picture level look like this, and this is the original picture. So this is actually a prediction, and we clean up like this. So and this is the confusion matrix. You can see it's not that bad. It's acceptable, operational acceptable. So although the sample size is not big, but you need to know that not every state has a ball seed event. So it's tough to get so many label data. So this is the second model. The third model is the slurry rate. So this one actually is not ML model. It's just like we want to quantify the states. So we want to quantify the states which the ramp up, the green one, ramp down, the blue, the red one, and also the plateau, the blue one. So this one we can know that how many percentage of time the flag pressure is in the peak or the slurry rate in the peak. So here you can see that compare these two states, maybe this one is better because this one almost majority of time, like 50% of time, actually is in the peak, but this one not. I don't know, but just the idea why we build this model. To try to, but this is the procedure we do. We use a very traditional signal processing method, several ones combined together. Go through this one and go through this one, and finally get this one. So if you want to know more detail, we can just go to this paper. And this is actually one model. Let me see what else. 37, still good. And next one is Welhead pressure. Welhead pressure prediction. We use a deep learning model to predict the Welhead pressure during flag jobs. One, let's say we want to see predict the screen out, because if the pressure jump crazily, then it's a screen out. And also we want to pay the foundation for the next model, like the cost optimization. That's the big cake. So actually we try 3 kind of methodology, and the RNN, CNN, RNN in the middle, and the MLP, the more tuple layer prediction, something like that, so in the right. So when we actually try to deploy the model, the MLP actually is the most lightweight method. It's similar to what I said before. When you want to deploy a model to a real-time application, the calculation time is more important. So the MLP is always get the result very quick. So that. And here we use a concept for continuous learning, also called online learning. So because when for the FRAC job, actually is very unique, different from other. We cannot use other states data to train the model and predict in this state. So what we did actually is like we need to continuously update and retrain the model with the new data. So let's say from here, you see you had the training data, test data up to right now, and you build model 1. And then when the new data come in, you use the old data as the training data, this new data as the test data, and you train the model 2, and then in this way you update the model. So here we retrain the model every 2 minutes, and we predict the next 2 minutes. So that's compared to the edge computing. So this is a job back in the cloud. Ideally should deploy in the edge, and then because the latency from the data from the cloud or to the edge to the website kill this 2 minutes prediction. For example, let's say if you can predict 2 minutes, but if your data move from the website to the cloud, take 20 seconds, and you do the calculation and get the result, and you go back to the ground, and then it take another 20 seconds. So actually you waste 40 seconds. And you have 2 minutes prediction, like 120 second prediction, but finally the predict power is 80 seconds. So that's why I say it's killing this model. So this actually is a GCP workflow. So you see, you get the data, you do the training, you do the prediction, and then you wait 2 minutes, something like that. So that's one of the drawback of the cloud. Here's the result. Result look like, you can see that actually these are RMSE. It's good. No, it's good. And here for this is actually is like the UI we have. So the dash one, like here, this is actually the prediction. The dot text red light is the prediction. So I will go to the last model. So last model actually is the really big cake. Really big cake, that means we want to do a cost optimization real time. So this model assuming to assist in the completion engineer to adjust the pumping schedule to optimize the completion cost on the fly. So for the completion cost, of course, the different company, different service company, they have different cost structure, but majority is driven by the horsepower. The horsepower actually is represented by the Welhead pressure or like the slurry rate. So the higher the pressure, the more they charge you. So the good strategy is that you need to keep your Welhead pressure in a stage, like 8,000 psi or 9,000, but you still need pump the sand into the hole with the like half hour. So that's the logic. So that's why give us the chance we can optimize. So first, we use like before, we use the deep learning to do the prediction of the wellhead pressure. Here they use a linear transformation function to predict. It's still pretty good, you see, but they also update the model every 5 minutes. And then after that, they use the MPC to do the desired optimal schedule. MPC, I will talk about that later. And once so when you set the target for the well pressure, let's say 8,000 psi, something like that, then you manipulate other variable to achieve different scenarios, so as to save the cost, depending on the cost structure. So I will explain a little detail in later. But manipulate, that means you can change the slurry rate, you can change the concentration of the sand, or like the friction reducer, that kind of stuff. So you still keep the wellhead pressure not going up, And at the same time, you can reduce the time to pound the sand. Let's say originally it's 30 minutes to do the job, but you do it in 20 minutes. That saves money, right? So that's the logic behind here. This is the MPC. MPC was MPC. MPC is like, okay, here the black one is what we want. So that's the true one, is the black one. But this is the future. We don't know this black one in here. And what we use is we use the predict one output, the yellow one. Yellow one we predict like we predict before as an input. And also the blue one actually is the control input. This one will change this one. So because we use the yellow one to mimic the black one, so the MPC will tell you how to change the green one so that you can get the yellow one. So that's the logic. So that's the logic behind this model. You predict the well pressure, and then you use that as input into this model, and model will tell you that, okay, you need to either reduce the concentration of the sand or like the slow rate, something like that. So that's the logic. Here is more clear. So you can see here. So start from here. You get some data, and then you build the wellhead pressure prediction model. And then is the pressure going up quickly? Then that means it's skin up. If yes, then you need to cut sand, right? If not, then you're good. You come to the MPC optimizer, and then they give you tell you how to manipulate this variable. Manipulate variable is the U1, U2, U3. You change this one, so you still keep the wellhead pressure as you predict, right? And then, but you can reduce the time or reduce other stuff, so you can save the cost. So that's the logic behind this one. Behind this one. Okay, let's see. Okay, the last one. Do I overrun? 45. So this is the last slide. So the WPS analysis, the WPS real-time analysis strategy. Actually, we try to. Right now, I'm in WPS. I try to rebuild the real-time system. So we call the in-series system. In-series, that means I'm in the innovation team, so we put everything in front of everything, the in geo, in frag, in product. So that's what I'm doing right now. But I will do it in a different way because I get the lesson learned from APC, and then the one I'm going to build actually is we use more open and advanced real-time technology or platform. Let's say before I use a Streambase as a streaming platform, it's very expensive. That's the lesson learned. And then also it's not very open, like it's a closed source one. But if you use open source one like a Kafka, something like that, then you have more momentum to upgrade the technology. Another one is the cost. Like the cost is like the cost to build a system and cost to maintain the system. So like in my previous one, it's very expensive. But in the market, they also some of the vendor provide the same service. So our solution, internally solution, still need to be cost competitive to the outside solution, so that we can build, not buy. So it's always build and buy. If you build, you're supposed to be a cost not higher to that, we still can build it. If it's too high, then you buy it. So I'm right. So that's the second lesson I learned. And also in the third one, I can able to deploy the hardware to the edge, so we can do edge computing. So that's a true real-time decision making. And also in the future, like the closed loop control. That means like the Julian, you hook up with the Luke control system and you do some algorithm and let the Luke do the well automatically. Of course, that's far from right now, but we need to be open for that. And the last one is like I want to be more practical, so I want to build more useful and model, not like focus on the model which is just fancy, but doesn't have that much business value, because this kind of model, PPT model or PowerPoint model, is like the model is only sit in the PowerPoint, never go to production, bring value to the company. So that's the third one I try to avoid. And then we are still ongoing, so we are happy to share with the industry in the future once we have something solid internally. Yeah. So I think that's my presentation up to right now. Let's see. I'm good. I think I don't overrun the time. Thank you. Back to the host. Right.
Hey, I have a quick question. So, given that your real-time system, you have the total system is where you have different inputs coming and you have certain actions that are happening based on what your models say should happen, taking into consideration the input. Before you deploy these systems in field, how do you test that total system, whether it is working properly or not?
Oh, that's a good question. Yeah. So actually, we do have a test system, and we had a test environment, and we have production environment. So actually, like let's say before I had all of these. Let's go back to the architecture. Where's architecture? Like here, we had architecture here. Like here, we had this one. So we have a system. Actually, is in a production. This is managed by the IT, and we have a test environment identical to this one. It's just for test the model and test the just for testing. So any model, we need to test continually like 2 weeks or 1 month to see whether it's good or not and change it. So yes, before we deploy the model, we do a lot of tests. Yep. Is that answer your question?
Yeah. Part of the reason I was asking that question is because of something that you said where you were talking about the data digitization and where you said, well, you built the model with 5 inputs, but then you found out that you have only 2 inputs.
Yeah.
So the question was, when did you find that out? Whether when you were doing this testing part, or whether when you were deploying?
Yeah, we do this in the testing part. We find out the issues. That's why actually this system, the first generation is online at 2017, but the second generation is 2018. So actually, I spent a lot of time building these two, because we built some of the model is not useful, cannot put into the production system because we don't have the data. So we need to actually build a lot of apps to digitize the data so that we can use the model. This is common in oil and gas. But if like in Silicon Valley, all the company only had 10 or 15 years of history, all the data is actually in the database. But oil and gas, like ExxonMobil is 100 years old, and then Anadarko actually is 60 or 70 years old at that time. So yeah, it's a good question. Thank you.
So Dean, so this is Kevin. Thank you very much for your sharing the last presentation. I just have maybe one question. So all of this kind of algorithms and models you're testing, did you get any chance to think about how that could be used for example, for the from drilling, completion, and then mapping up or visualization some like a fracture network as an application, or something related to the reservoir characterization? Is there any kind of insight you have?
I think at that time, I haven't touched the portion, but actually, I'm not sure I answer your question, but let me put it this way. So at the time when we back to Anadarko way, we do want to use the during data to inference some information so that we can design the completion in a good way, because during data you already have, you drill the well before you frac the well, so you have some information. And also we try to integrate some of the geologic data so that it makes us a whole system. But my focus is all in the completion and drilling, so I actually not touch the reservoir side. But yeah, they do have some of the idea, but haven't put any get any value result out of it. I'm not sure if that answer your question.
Yeah, that's right. Thank you.
Yeah.
Hey, I have one more.
Go ahead.
Sorry, go ahead.
Thanks for presentation. So I just have one quick question. Deep learning is generally very susceptible to bias. Once you learn with bad data, it's practically impossible to untrain the network. How do you ensure no bias is introduced during training? So, for example, it doesn't propagate to the inferencing stage.
That's right to the point of this model. So this model actually, yes, and especially is very important when you train the model for 2 minutes and uses another 2 minutes. It's very demanding. Actually at the time we do a lot of the test, like we quantify. When you read the paper, you will see that we quantify a lot of uncertainty, and then we try to find a way to metrics say that, okay, this model is good, so we can use to do prediction. Because actually this is running automatically. You train the model, your users, you train the model. How do you know that your data in this phase is good, so that your model is good? Even the data is good, you don't necessarily you will train a good model, right? So we do have something, but we haven't made this to a production level. So it's just a test and a POC. Yeah, that's an open question, and it's very interesting. And for the data quality side and also the model uncertainty side, there needs to be a lot of work to do. Yep. It's a great question. Yeah.
So I have a follow-up on that one. You know, as you're collecting more data, let's say take the drilling example, you know, you're collecting data at a particular location, and that data that you're collecting is reflecting what's happening at that location, which is, you know, characteristics of that location being, you know, translated into data. As you move forward, as you drill deeper, let's say you go into another formation where you're going to have a completely different set of parameters that's going to affect what's happening over there. So now the question is, how are you going to trust the data that is, the model that is trained on something that was, you know, that is not necessarily completely relevant to where you are now? So why are you adding that data when you're training your model when you're at a new location?
Yeah, so that's actually you see I know where so you see my screen right now. We have the blue the green portion here. So yeah, that is exactly. I think from the same well, it's not the big problem for the same well. Like I told you, we build the general model for 3 basins, still good, but we still want to build a mechanism to monitor the model, whether the model is running good or not. So this ML pipeline is actually what we did. So actually this ML pipeline, actually what we do is we build an online model. That's a real-time model. And also we build an offline model. Online model, when you build a model, you only know the information up to right now. So it's very demanding, right? Like say you don't know the next second one. So you build a model. But offline model, actually we use all the information we can get. It's a statistical data. So actually what we did is that we consider the offline model is more accurate than the online model. So that in the day, every single section, we use the online model to run for inference the data. But in the middle of the night, we will use the past 1 day's 24-hour data put into offline model and do another prediction. And we compare the result of these 2 models and see whether they are consistent or they are disagree. So if we see that, okay, 5% or 1% or 2% of the data, the result is different, then we think that maybe we will get an alert that say maybe the model is needed to update, all right? So if that case, then we need to retrain the model and redeploy the model. So that's actually the green portion here. I didn't go into the presentation today. It's because it's too much. And then it's just a POC. We haven't put this into production at the time. But unfortunately, Oxy come in and we stop everything. So is that answer your question?
Yeah, I kind of got a sense of it. Thanks.
Yeah, so the paper will have detail.
Sorry. This is Fred Anazada from FACT. I have 2 questions. One is, have you used this method for some sort of geosteering or similar technology that Schlumberger has on Periscope and basically characterizing reservoir properties as you're drilling?
No, geosteering, we haven't touched the portion. It's in the plane. But another question is like we don't use any third party. I know Schlumberger do a similar stuff, and also maybe like in the market, you know, Cova is the same one. So no, but I do have some friends in the Schlumberger. They did some great job, and I'm very interested. So yeah, but we don't have any chance to collaborate with them at that time.
Okay. The second question I have is. I know you mentioned that you are doing some signal processing, and whether you use any type of mud pulse telemetry to get some subset of the data that you might use in your analysis. And for example, do you have to do kick detection as you are doing the drilling?
Your voice is cut a little bit. I'm not sure I get your question. You say, do I use any signal processing method? Yeah, we do have, but we just use some of them because some of them we don't have the patience to use it because some of the signal processing, the traditional method, is take time to turn the model to the way we want. So a lot of time we just use the deep learning because the open source one, we just get the open source code, we label the data, we try it's working, then we use it. It's like faster and we can solve the problem in 2 weeks. So yeah, we use some of them, but we don't use too much. That's my, did I answer your question?
Yeah, actually my question was mostly on kick detection.
Kick detection.
Talk about using this method or one of the methods for kick detection.
I haven't do that. We do have that in our roadmap, the kick detection. Yeah, that's a very hot topic. But we haven't made any good model to do that in a production level. I know that in the SP paper there are a lot of paper on that, but I'm not sure how actually they are working in a automated way and a sustainable way. I say kick detection in a real time. Say that is actually in a production. Right. Yeah, we haven't did that.
That's when you need that's when I was talking about using signal processing techniques that can use mud pulse telemetry data in real time to do the kick detection.
Yeah, I think that's is in our list at that time. But I haven't had a hand to touch that one. Kick detection is a lot of business value, and also I think it's not that difficult. But it's still challenge, trust me. It look like simple, but real-time system and offline analysis is different. Like you say, you get a bunch of data, you analyze, you evaluate the model is good. But even in that time, when you want to deploy the model in a real-time system, sometimes it's not that story. So that's my feeling. Yeah. No, at that time. Yep. Go ahead.
Thank you.
Yeah, thank you for the question. Great question. Any further question? It's 2 o'clock right now. No question, then let's hand back to the host.
Thank you. Yes, thank you. Thank you very much for an excellent talk. Really appreciate your sharing your information with us, and thanks to everyone for joining on this discussion for the good series of questions. And hope everyone has a fantastic weekend. Appreciate it greatly.
Thank you, Grant. You have a great day too. Thank you, everyone.
Thanks.
Bye.
Yep. Bye.